welcome back to Yebo Tutor. Good afternoon, and how are you doing? I hope you're well and you are doing your practice for your tests and exams. And some are already writing, so all the best. I wish you very high pass marks. Right, so what we are going to finish off today is a question on electrochemistry. We started that question last week. We went through probably halfway, and we always had some homework for you. Did you finish off the set of questions that we were about to work out? Did you try out something? I hope you did. I hope you also found some answers and you now are getting comfortable with your electrochemistry. We are working out a problem on a galvanic cell, isn't it? It's a galvanic cell, and it is made of two half cells, cell A and cell B. This is an attempt on question number 8 in the 2021 paper. That's 2021 paper 2, which is this one, grade 12, 2021. As we worked out some questions last week, I think we also came across an electrochemistry set of cells. So we had a galvanic cell, and then we also had an electrolytic cell. Right, so let's just see the galvanic cell that we saw before we started working out. Still remember this one? Do you still remember it? Yes. That was the first galvanic cell that we worked out. Two half cells, zinc sulfate, copper immersed in the copper sulfate, zinc immersed in the zinc sulfate. Then we've got a potassium chloride salt bridge. We measured the potential difference, V, and then we can get to see the actual motion of the particles in this cell. Then we looked at an electrolytic cell. So here we are performing some electrodeposition, isn't it? We are purifying this material which has some copper in it. And we're using copper sulfate, and then we actually found out how you can determine the potential of this power supply unit. Right, so that was the first set. So what I'll do is to now scroll to this question. We are on question number 8, and that is what we need to finish out today. Let's just scroll all the way down to question 8. There we are. So in question number 8, we already stated the energy conversion process. We already calculated the mass of the silver nitrate. Do you still remember that? Yes, we also looked for what was missing in the cell. I hope you still remember that. So we said if we want to calculate the mass of the silver nitrate, we obviously need to collect our data first. We have a volume that was supplied, and then we converted it to our dm cubed, our liters. And then we've got our concentration, which we use to determine the formula for mass. And we also said we can find this formulae in our data sheet. Then we went all the way to calculate the actual mass by simply substituting, isn't it? We substituted the standard concentration, 1 mole per dm cubed. We substituted the molar mass, which is the sum of the relative atomic mass of silver, nitrogen, oxygen, right, in their appropriate stoichiometric ratios or quantities. Then we also had the volume, which we already found earlier, and then we came up with the mass. Now that you have the mass, the next thing would be to identify the reducing agent. We did that last week. I hope you still remember how we did that, because the next question actually needs you to use that concept. So this was the question number 8.3, which said define the reducing agent. Define the reducing agent. So we've got the term reducing agent, and we already defined it there. It simply donates electrons. When it donates electrons, that's a minus. It gives a negative charge. If you give a negative charge to something that is negatively charged, you're actually further dropping its electric potential. Same applies. The reverse is true. If you've got a species that are positively charged, and then you supply a negative charge, you actually reduce the quantity of their positive charge. So it can still be positive, but less. So that's the reduction process. So a reducing agent is just an electron donor. And then the next thing now is question 8.4. So let's home into question 8.4. 8.4, the first part, which is 8.4.1. 8.4.1. 8.4.1 is asking for the following. Name or write down the name or formula of the reducing agent. Write down the name or formula of the reducing agent. What are we talking about? We are talking about this electrolytic cell, this galvanic cell, sorry. We are talking about this galvanic cell. The galvanic cell, we said it contains two half cells. It's made of two half cells. This is the copper half cell in copper sulfate solution. Is it copper sulfate? No, they didn't tell us what it is. So, sorry. Copper sulfate was for the other question. So this is in a salt of what? Of copper. And then we also have this silver in silver nitrate. So the silver is what we know is in silver nitrate. So the question is, what is the name of the formula of the reducing agent? You've already identified which is the reducing agent. In fact, you have identified the definition of the reducing agent. So the question is, which of these is the reducing agent? So that you can state down the name or the formula. Right, so how can we do that? What is the approach that you can use to name the reducing agent? We now have two to consider. We've got our silver and copper. So which of these is the reducing agent? Right, so let's just look at our electrochemical series. Let's look at our electrochemical series. This is in our data sheet. So it's somewhere further down your question paper, close to the end. Then you've got some formula sheets and all that. Then you've got your periodic table. And this is our first format of the standard reduction potentials table. So table 4A will list them in the following way, where our positive potentials are right at the top. So this is where we're increasing in oxidizing power, isn't it? Increasing strength of oxidizing agent. So we are actually upward for the oxidation. Now, this means in our case, between copper and silver, where is silver? Let's just blow this up. This is our silver. This is our silver, right? And that is its standard reduction potential. Where is our copper? Let's maybe check here. Where is our copper? Where is our copper? We've got this ion here is for what? For copper 1, isn't it? Cuprous. So this is the cupric ion. There goes the cupric ion. And we have it all there. There we have it. Now we're happy. So I think we already did this, and we have identified that on our left hand side, the increasing strength of reduction. Look at that arrow. The increasing strength of reducing agent is downward. So between these two, the species that are stronger in reduction, it's copper, isn't it? So it's obvious that in terms of the name, then you are using copper, right? How about in terms of the symbol? We said a reducing agent is a what? Is an electron donor. It's an electron donor. So if it is an electron donor, look at this chemical reaction. In which direction can we consider this chemical reaction in order for us to literally donate electrons? Can you see that? We would need to look at this chemical reaction from this end, right? That is The only way our chemical reaction can result in the addition or the donation of electrons into solution. Do you get that part? So this means that the copper that we're considering is the solid copper, which is which one? This one. This is our reducing agent. Right. Does that make sense? Does that make sense? Let's go through that again. How did we arrive at this reducing agent? We arrived at this reducing agent by using the electrochemical series. What we were trying to do is to name the reducing agent or write down the formula of the reducing agent. So we had to use the electrochemical series and identify which has the stronger reducing strength. We identified which has the stronger reducing strength, and we are good to go to the next question. So can you please come up with this balanced reaction? I will give you a few seconds to come up with the balanced reaction, then we can continue. Let's see that balanced reaction. right? Which of these three formulae is appropriate for this calculation? Which of these three formulae is appropriate for this calculation? I am seeing that this calculation was carried out without sound. So let me just remind you that in half cell A, what we did was to write down the chemical reaction to show that copper is actually dissociating and donating electrons, because it is the reducing agent. So it is donating electrons. That is why we wrote this chemical reaction in this direction. Then in the second cell, half cell B, what we were looking at is the second equation, where we have the silver. So the silver equation, we had to balance it. Why? Because in this reaction, the 2 electrons donated by the copper are the electrons that will actually reduce this silver ion. So how do those electrons reduce the silver ion? We actually have to transfer them from the solution through the external circuit, and then we have the 2 electrons seated there, and the silver from the silver nitrate is reduced until we have the silver solid material. And by the way, we should have a 2 there so that our silver actually balances on both sides. So this is our chemical reaction representing the process. That's the chemical reaction representing the process. Next is to find the initial EMF of the cell. So our symbol there is E theta of the cell, the initial EMF of the cell. And this one, I'm sure you remember, this is at standard conditions. So let's hear from you. How can you find this initial EMF of the cell? How can you find this initial EMF of the cell? Let's get onto it. Right, I think we've seen what we can do. We've identified what to do there. Which equation works? Which equation works? So from what you have tried out, let's see the format of the equation, because the equation has been supplied, isn't it? So you just want the format. How does the equation look like, and which is appropriate for our case? The first one is an equation that reads E cell is equal to E cathode minus E anode. E cathode minus E anode. Which is the cathode? Which is the anode? Which is the cathode? Which is the anode? So that's the question to ask oneself. So tell us which is the anode, which is the cathode of this galvanic cell. Next is E cell is equal to E of the reduction equation subtract E of the oxidation equation. Okay, so which was the reduction equation? You simply go on to the electrochemical series and you pick the value of the reduction process. Right, so let's just see if we can identify the reduction process. Right, there we have our reduction process. This silver is being reduced, isn't it? That's the reduction process. So E reduction is our E for the reduction process, and then minus what? So let's actually write it down, minus E oxidation. So that's our E cell. E at standard conditions of the cell is equal to E of the reduction process minus E of the oxidation process. E of the oxidation process. Right, so we have already seen that the reduction process is what the silver is going through. This is the reduction process. So that's our plus 0.80 volts minus E of the oxidation process. This is our oxidation process. Can you see that? So that's our oxidation process where our copper, its oxidation number was actually increasing. So that's our plus 0.34 volts. So in the end, what is 0.8 subtract 0.34 volts? What is 0.8 subtract 0.34 volts? So that's your 0.80 minus 0.34 volts. So your E cell is coming down to plus 0.46 volts. This is your E cell. Right. Let's try the last equation. Let's see if the last equation is sensible. Let's see if the last equation is sensible. The last equation says, E cell is equal to E of the oxidizing agent minus E of the reducing agent. So this is about the agents now. So let me just look for some more space. Right, let's just look for some more space. Add a page there. Yes, please. There we have it. So, second formula, we said E cell at standard conditions is equal to, it is equal to E of the oxidizing agent, E theta of the, let me say, ox agent, and then subtract E theta of the reducing agent, which is the oxidizing agent. So can you see, it depends with what you're comfortable with, right? The formulae are supplied so that you can get to actually think about how you can end up defining it for yourself. That depends with what you are comfortable with. So we've already said, in this process, this is our reducing agent. This is our copper, our reducing agent, reduction agent. We already defined it and identified it. And then our silver is the oxidizing agent. Oxidizing agent. Right, let's just say agent. Like that. And also do that here. Right. So what we have seen is our oxidizing agent has an electrode potential of 0.80 volts. And then our reducing agent has an electrode potential of plus 0.34 volts. And as you can see, this is the same as this calculation there. So our answer must be plus 0.46 volts. That is our E cell. That is our E cell. If you would like, you can actually come back to the equation that we used to balance this process. Can you see this process? For us to come up with the left-hand side, which is this side, all we did was to add these left-hand sides, isn't it? for us to come up with the right-hand side, all we did was to add up all the right-hand side species, right? As you can see, we would have the 2 electrons here from this part. We would have the 2 electrons there from this part. So, other way, 2 electrons from this part, and then 2 electrons from this part. So we have 2 electrons on both sides, so those would obviously cancel out. If one of the 2 electrons would move to the other equation, then they would become negative, and then we don't have. So that's why we don't have the 2 electrons in this part of the equation. So since we've been adding everything, you may as well add that up. Then you will get your what? You'll get your E cell. So how do you do that? Minus 0.34 plus 0.80. What does that give you? What does that give you? Can you see it's the same thing that is on our calculator? It's the very same thing that is on our calculator. You would get a plus 0.46 volts. So basically that is how you can carry out your calculation. Let's also see the first equation there. We said E cathode and E anode. So which is the anode in our case? Which is the anode in our case? So can you see what's happening here? Which is the anode in our case? So we are seeing that what actually happens at the anode? That's a good question. What happens at the anode? At the anode, we usually have, let's say it's an electrolytic cell, right? At the anode, we have a positive potential of the terminal or of the electrode. If it is positive, usually we have negatively charged ions that reach the anode by electrostatic attraction. When those ions reach the anode, what happens? They are oxidized, isn't it? They are oxidized. Their potential actually increases. So in our case, can you see that the silver is immediately being, it's appearing as our terminal that has the positive potential. So you'll see that in a galvanic cell, we're actually looking at it in the reverse of an electrolytic cell. So in this case, we actually have the positively charged particles that are carrying out the reaction on the terminal and building up some material on the terminal, and these are on the silver. So once again, you would then find that your silver potential is 0.8, and you subtract the cathode potential, which is the copper potential. Right, so I think that has come to an end as far as the question, that part of the question is concerned. So that's the initial EMF of the cell. Now, question 8.6. May you please attempt it? Question 8.6. Question 8.6. How would you find out this one? So question 8.6 asks as follows. How will the EMF of the cell be affected if the concentration of the copper ions in half cell A increases? If the concentration of copper ions in half cell A increases, how would the EMF be affected? Does it increase? Does it decrease? Does it remain the same? Let's reason it out, and you tell us. Right, so let's figure it out now. We already know that our copper is increasing the what? The amount of electrons at this terminal. So our copper is leading to a buildup of electrons on that terminal, and the electrons are conducted, isn't it? They are conducted to that other end. We also know that the chemical reaction associated with the copper reduction is this chemical reaction. That is the chemical reaction associated with the copper oxidation rather, so that we can have the silver reduced. So if we have a lot of these, right? If the concentration of the copper ions in half cell A keeps increasing and increasing and increasing, isn't it? We are going to get to a point where this silver, what's happening to the silver? The silver keeps getting reduced, right, into a silver solid. So we keep reducing the silver, we'll get to a point where the silver is now what? Is now exhausted, or it's been consumed from the electrolyte. So if it increases, the copper ions increase, then this chemical reaction with this potential is going to become the active chemical reaction. So what happens if we have our negative potential continuously present while the positive potential is continuously getting less and less? So we are going to have a reduction, isn't it? We'll have a reduction. So just think about it. This process, you are going to end up getting a decrease in the potential. Why? Because this process that keeps continuing in half cell A actually has a negative potential. So in our case, if we keep increasing the concentration of the copper ions, we get to a point where the potential keeps decreasing. Right, let's just see an animation of this. Let's just see an animation of this process. So we will go into teachchemistry.org and they have a voltaic cell. So this is our galvanic cell. Let me just copy that link and share it with you. So try out this reaction. So try out our our galvanic cell set up on this tool. Try out our galvanic setup on this link. So let's just send you that message. Let's just do that. Type it here. Right, and then I can paste the link, right? Let's paste the link so that you can try it out. Right, there we are. So if you visit this link, you will be able to see our setup. This is our galvanic cell. We have not yet put anything for measurement. That's why we don't have the top part. So let's just see our diagram and see how we can actually simulate this and see it in a virtual laboratory. So this is our galvanic cell, right? So what must we have? We must have in the left beaker, we must have some copper solution. So it must be a solution of copper with some, so it's a salt of copper, isn't it? On the right hand side, we already know that we have silver nitrate. So let's actually put on the right beaker silver nitrate. So we have a silver nitrate there, and obviously this is now silver metal, isn't it? In fact, here we don't have silver metal yet. It will build silver metal, yes. Then let's put a copper salt. So there is an option for copper nitrate here. So we may as well use that copper nitrate. So that's our copper in copper nitrate in the left hand side beaker. So look at what they've done. There is a terminal here that is in red. This terminal here is connected to the red point of this meter, isn't it? So this is a meter. Then we've got a black terminal there that is connected to the negative terminal of the meter. Remember, this is a galvanic cell, so it actually is going to generate some electricity for us. Now, the only thing that you can do in this setup is to switch on here. So right now our setup is still off, and we are hoping to see what. The potential for this chemical reaction, which is on the left beaker, is A minus 0.34, isn't it? The potential for this part of the chemical reaction is A plus 0.80. So the total potential we expect to see here is going to be actually a plus 45 from the calculation. So let's switch it and see if it will work. There we go. So in this setup, we actually have a minus 0.46. So let's see what we have in our cell. Let's see what we have in our cell. Let's see what we have in our cell. Right, I think the terminal is there. Let's just see the terminals there. Let's see what we have in our cell. Can you see that in our cell, we have our copper on the left, isn't it? Copper on the left. Okay, good, that's fine. So what we're actually seeing is that the meter has been connected in such a way that we have our positive terminal connected to the copper, isn't it? We have a positive terminal, which is the red terminal, connected to the copper, and then we have the negative terminal connected to the higher potential point. We always know that with our units of measurement, with our voltmeters, the red terminal is connected to the higher potential point. The black terminal is connected to the lower potential point. So for this reason, we get to actually see a negative 46. In other words, if we were to take in our left beaker, which is this one, and we put in our silver nitrate here, which has a potential of what? Silver nitrate has a potential of plus 0.8 from this reaction. Can you see that? Plus, this is the point of higher potential. So if our meter were connected here, then we would find a plus 0.46. So let me just switch the copper and the silver so that you can see what we're trying to say here. Can I change these terminals? I unfortunately cannot change these terminals. Okay, so I will change the silver and the copper. Let's just see, can I do that? Okay, maybe let me change the species here and then put silver there, then put the copper here. Okay, so what I've just done is to switch so that we have our silver, which is in the left beaker. The left beaker, we expect a higher potential. That is why we can end up getting our 0.46. The correct value is actually plus 0.46, right? From our calculation we've seen using the formula, it's plus 0.46. So what is happening here has to do with the terminals on this meter. Right, so that covers our question. We also said that we would like to increase the molecules in the copper. Let me just see if we can we do something there. We can't do anything there. All we can see is that in the copper cell, the right beaker, on a molecular scale, we just have the copper dissociation. Can you see that? These are the copper ions that are dissociating. So these are the copper ions dissociating into solution. And what's going up? What is going up? What is going up are your charged particles. So that's your electrons going up into the what? Into the external circuit. Then on this silver, the electrons arrive, the silver ions will attach. Can you see that? The silver ions will attach and become silver atoms. So that is our process. Let's just see this same process in this kind of a standard deduction cell. So I think here we can select. So what we want is let's do some comparison in the first place. So this is our copper ion solution, and we've got our hydrogen reference, right? Copper ion solution, and we are seeing a a plus 0.4 volts for the copper ion solution process. So this is what? This is reduction of copper, right? And then if we were to put our silver, there's our silver, that's our 0.8 right there. So let's now put our copper on the other terminal and see what we will get. So that's our copper on the other terminal, and this is now our process, right? This is now our process. So this is what would require, if we had a meter instead of this cell, that's when we can actually measure that voltage. But otherwise, this is our copper, these are the electrons. You see the electrons all the way. And then the silver, which is in solution, is being reduced to silver solid. And then we also have, obviously, the salt bridge, where we have the negative charged particles traveling. And the negatively charged particles, can you see? They're actually pulled to this point as we have more positively charged ions here. So there's an electric field there. Right, so we have completed this question on electrochemistry. We have finished this question on electrochemistry. This, I think, will sum up our practice problems for this part of the term. It will sum up the practice problems. So I would like to once again wish you the best. I hope you remember from this electrochemical cell, which is made of 2 half cells, what has been taking place and what you will need to work on later on. So this is to wishing you the best in your papers and all the other subjects. I hope that you will get the highest of marks, not out of just repeating or just cramming. I hope you get the highest marks out of demonstrating your knowledge on paper. So all the best in your tests. It is goodbye from me. I wish you all the best this year. Thank you.